with the last talk of this session. And let me present Ries McCurdy from UNAM, right? From the
From
Institute of Mathematics, new coming collaborator. So, and he will talk about some recent advances in varifold regularity.
Very much. Thank you for the kind introduction, and thank you very much to the organizers. It's a real pleasure and an honor to be speaking here after so many wonderful talks. Before I begin, or rather as a way to begin, could I ask people to raise their hand if they have heard of varifolds before? Excellent. This first slide is for you. What is a varifold? What are varifolds? The name comes from the attempt to produce a class of generalized manifolds, right, that were appropriate or had good enough properties to do calculus of variations with in order to run geometric variational problems with. And I think perhaps one of the best ways to introduce them is to look at one of the sort of most famous and classical geometric variational problems, the plateau problem. Suppose we have some curve or some, well, classically just some curve in Rn, and the question posed, I believe, first by Lagrange in 1760, but then maybe 100 years later by Plateau, is, does there exist a minimal surface which spans that curve, right? So it's a problem of minimal surfaces, and certainly lots of progress was made from this, starting in 1760 with the work of Lagrange, but skipping forward in time to the 1930s, right? We finally got really good solutions to the classical plateau problem. First 1930 with Rado, who solved the problem for any rectifiable simple closed curve, where here rectifiable, I just mean a curve of finite length. Right? And then a year later, Douglas, using a different method, solved the plateau problem. He proved the existence of two-dimensional minimal surfaces for arbitrary simple closed curves. Right? And this won him the first Fields Medal, I believe, for Douglas. But this, of course, leaves open lots of questions, one of which is, what if you're not a simple closed curve? People were very interested in this, started working on higher genus versions, but perhaps more subtly, and more importantly, both of their works really relied upon complex analysis, right? They're doing two-dimensional minimal surfaces. They relied upon things like isothermal coordinates, and therefore their techniques do not go through in higher dimensions. So the big question for a long time was, how do we solve a higher dimensional version of Plateau's problem? Jump forward 30 years of work, and suddenly we had many, many solutions, sort of all at once. The first was Federer and Fleming in 1960. They solved Plateau's problem in all dimensions and codimensions using a framework of rectifiable integral currents. We will talk about what that means in just a moment. Same year, Reifenberg also solved the Plateau's problem, also in all dimensions and codimensions. And was able to obtain some very interesting regularity theory using methods completely different from what we will talk about today. And he was using a framework of compact subsets, right? Just compact sets as your sort of spanning set. A year later, DeGiorgi solved Plateau's problem and obtained some really powerful partial regularity results in the class of oriented minimal hypersurfaces, where he was using Caccioppoli sets or sets of finite perimeter, where the boundary would be his sort of model for the minimal hypersurface. In many ways, the class of rectifiable integral currents is a generalization, it's a more general framework than Caccioppoli sets. But these two are very closely related. And then only a few years later, Almgren solves Plateau's problem in the framework of integral varifolds. So suddenly we were awash with ways to solve this problem that took about 200 years, more or less, to solve. And before defining integral varifolds, I want to start with rectifiable integral currents, because this is a very popular framework, and there's a lot of work in it. And I think that the strengths and limitations of this framework really highlight why varifolds are a very natural setting in which to solve Plateau's problem, but also other variational problems, relative isoperimetric problems under volume constraint, things like double bubble problems, lots of these geometric problems. And I promise there will be PDEs coming. So that's the 60s. So rectifiable integral currents, this is just a bounded linear functional, right? T, it's going to act on smooth M forms. And how is it going to act? Well, by friendly integration. We have some disjoint subsets of oriented C1 subsurfaces, right, of the correct dimension. If we have an m-dimensional rectifiable integral varifold, we want them to be m-dimensional C1 subsurfaces. And we've got some weights, and we're just going to add up all of these integrals. Very friendly process. We all know how to integrate. And if we want these to be rectifiable integral currents, then we want these weights to only take values in the positive integers, right? And this is sort of their model. There's a notion of mass that comes with this, which, because we're just a bounded linear functional, is basically the operator norm or the dual norm on the space of smooth M forms. And then, of course, because it's just integration against some sets, we can take perturbations, right? So ambient deformations of these sets and track what happens to the integral, and this gives us a first variation, second variation. So it's a very good framework for doing the calculus of variations. But there is a problem, which is we assumed that these are oriented subsurfaces, and this allows for cancellation effects. We could have just two M-planes oppositely oriented, and as they get closer and closer in the limit, they cancel out, right, because they have opposite orientation. And this means that you can lose mass, and therefore the mass that comes with your rectifiable integral current, the thing you want to think of as your higher dimensional area, right, that you're minimizing if you're trying to solve Plateau's problem, that this is only lower semi-continuous. It's not continuous with respect to sort of convergence in the natural sense that comes with these currents. And a related phenomenon is because of this loss of mass, there's no Paley-Smale condition possible in this class, and that means there's not like an easy, obvious way to get a good mountain pass theorem, and therefore rectifiable integral currents are an excellent framework for dealing with area minimizers, like true minimums given a fixed boundary. But they're not so good for just critical points. That's what I mean by stationary. They're not so great for stable, which might be just a local minimum, or indeed sort of a Morse theory of these generalized surfaces. And another, in some sense, shortcoming, and in some sense, incredible strength of the framework of these rectifiable integral currents comes from what happens when you look at the singular set of minimal surfaces. Combining the work of a very large number of incredible mathematicians, we can summarize the work from the 60s, 70s, and 80s as if we have some area minimizing rectifiable integral current, so a true minimum, some solution to Plateau's problem, and I'm going to assume that it's n-dimensional in n+1, so it's a minimizing hypersurface in this sense. Then if n is less than 6, there's no singular set, right? You don't see, every time you zoom in, you get a flat tangent, you're locally the graph of a smooth function, right? But at dimension 7, suddenly the singular set can exist, but it would only exist in isolated points. The blow-up profile for this is the famous Simons cone, first identified by Simons and then later proved to be minimal by Bombieri and Giusti. And then if you're in higher dimensions, other things can show up, but you have nice bounds on the singular set. It'll be countably n-7 rectifiable. And this just means that it can be contained, like just set containment, in the image of countably many n-7 dimensional like C1 maps, images. So like C1 images of n-7 dimensional Euclidean space. So this is a qualitative condition that tells you that infinitesimally you always look like a C1 manifold. And all of these above dimensional results are optimal. This is an incredibly successful theory in one sense, and I want to be very clear about that before I talk about what I think of are the shortcomings of it. And the shortcoming is essentially that in lower dimensions, you have no singular sets. Singular sets can be at most like n-7 dimensional, right? But I'm going to try to convince you in a single picture why this is a bit of a problem. You have things that look like this, right? Classical sort of Y singularities. You have three half planes meeting at 120 degrees in between the planes. This locally is a minimal hypersurface. And moreover, this sort of thing shows up sorry for the very blurry picture of bubbles, but I love pictures of bubbles, right? You can see these triple junction points showing up in nature, and these are not allowed in the framework of rectifiable integral currents because there's no way to orient this. You can't go positive, negative, positive, oh wait, shit, it goes positive, positive. Like, it just doesn't work. And moreover, not only do you have these these n-1 dimensional singularities showing up, but these n-1 dimensional singularities might sort of converge to another point, and you also see n-2 dimensional singularities. These show up in nature. And admittedly, bubbles are a model for constant mean curvature surfaces, but if you were to blow up around one of these points, you should get a minimal surface. That's the intuition. So the framework for rectifiable integral currents does not account for these things. It has some problems with more calculus of variation perspectives about trying to do Morse theory, talk about mere critical points of the area functional that you're dealing with in your plateaus problem. And to solve these, right, this is what varifolds were invented for. So varifolds are a framework for geometric variation problems, which is good for Morse theory. It models real-world singularities well, and it also allows for anisotropic problems if you want to weight, if your tangent is over here, or if your tangent space is over here, if you want to weight that differently. And also more general elliptic integrants, things that are not exactly sort of surface area, but generalizations of this. Varifolds were invented to create the framework which would solve all of these problems, which rectifiable integral currents has troubles with. Okay, so that's the impetus. Now let's get like an actual definition. In some sense, they were introduced by Young in 1951, but then later formalized in Almgren's notes in 65 and popularized by Allard in 72. And an m-dimensional varifold is just a radon measure, friendly radon measure, some bounded Borel regular measure, like locally finite Borel regular measure, and it's a measure on your spatial domain omega cross just the Grassmannian of m planes, m-dimensional varifold, m planes in Rn, right, for your spatial dimension being in Rn. So it's just a nice radon measure. Of course, radon measures can be a little bit crazy, but under some very mild assumptions, all of which will be present for any of the geometric variational problems that are very popular, we can reduce to thinking of this crazy measure on this product space to just a coupling, a pair of some m-dimensional countably rectifiable set and some weight function theta, where now integration with respect to that measure, well, in the Grassmannian component, right, this is just the delta, Dirac delta mass on the tangent space of your rectifiable set at the point x, right? And then in the spatial component, it's just some weighted version of the m-dimensional Hausdorff measure restricted to that countably m rectifiable set. So very, very friendly, but there's no assumption of orientability whatsoever. And we're going to impose the definition. We're going to say it's a rectifiable varifold of dimension m in some ball in Rn if this theta function is just allowed to vary in the positive reals, right? So it could vary continuously, might depend upon it's going to depend upon the space. And we're going to call it an integral varifold if we restrict this this weight function to just be a positive integer, right? So this gives us a nice class to set up these problems. There's a native or sort of very natural notion of mass that comes with these varifolds, which is just sort of projecting away the Grassmannian component so that now you only see some weighted integral on some nice countably rectifiable set. And this is the notion of sort of m-dimensional area. Oh, typo, that should be in dimension n. And of course, we can do variations given some ambient deformations generated by some vector field. We're going to say that our varifold is stationary if the first variation, which is just the derivative with respect to t, evaluated at t equals 0 of the push forward of these measures, which is basically what happens under your deformation, if that's 0. So we have a critical point of the area functional as we're thinking of it. And we're going to say it's stable if it's both stationary, so a critical point, and also the second variation, so your second derivatives, are all non-negative, right? And of course, you can go further and develop a Morse theory for varifolds. People have done this. I'm not going to talk about that aspect today, but it is available. It does work out quite well. A few more definitions before we really get started on the PDEs. We're going to say that our rectifiable varifold has locally bounded first variation if this, as a functional of your sort of defining vector field that defines your deformations, is bounded. This means that it is a bounded functional on the space of compactly supported C1 vector fields, and therefore Ries representation theorem tells you immediately that you can represent this first variation as a measure. So you have first variation is representable by some vector integrated against a radon measure, which I will denote this way. And if you assume furthermore that that radon measure is absolutely continuous with respect to the mass, then you can rewrite your first variation as the integral of your vector field against some vector weighted by integration against the mass of the varifold. And this is going to be our generalized mean curvature. And of course, if you're a C2 submanifold, these all agree with the classical definitions, but it allows us to define things basically by integration by parts. And that's a much more general notion. Okay, so the game for varifold regularity, in some sense, is going to be thinking about analytic conditions on your generalized mean curvature and trying to see what geometric properties that will imply, and vice versa, right? It's this game between how integrable or how nice your mean curvature is, and then how nice the geometry of the support of your varifold is going to be. Okay, regularity theory. This will be a wildly incomplete overview of regularity theory for varifolds, and I want to start with the theorem of De Giorgi from his paper in 1961, where he was solving the plateau problem. And he proved that if we change from Caccioppoli sets to area minimizing rectifiable currents for a moment, that as long as you're a codimension 1 area minimizing rectifiable current, then as long as you have a flat tangent at a point, on the boundary of your Caccioppoli set or on the support of your rectifiable current, then you're in the regular set. And what that means is there's some neighborhood around which you're locally the graph of a smooth function. And we're going to call the singular set everything else. And this is a profoundly important regularity theory. It's often shortened to the idea of flat implies smooth. But of course, what flat means is almost flat. Implies means something much more like this. And smooth means just C1 alpha, right? To go from C1 alpha to actual C infinity requires Schauder theory, right? And his regularity theory really provides that first step in regularity to get to C1 alpha, and then Schauder theory takes it from there. So it's very helpful to consider what happens in just like a minimal surface that's given by a Lipschitz graph to see how this works. So if I have some minimal surface given by a Lipschitz graph, then I know that weakly I satisfy the mean, the minimal surface equations, and you can define a new function given by one of your directional derivatives, and you can work out that actually those directional derivatives satisfy the following divergence form equation, and, right, DeGiorgi's 1957 proof of Hilbert's 19th problem tells you that anytime you have a divergence form elliptic PDE, where your coefficients are bounded, elliptic, and measurable, right, then your function v, which satisfies this, has got to be bounded. For us, that's not very novel. V is a directional derivative. We'd already assumed that we are Lipschitz, so that doesn't give us much. But also then he proves that those functions have got to be Holder continuous, right? And going from bounded to Holder continuous is his famous sort of oscillation reduction argument, where he's using basically Sobolev inequality and then what's called a Khachapli inequality. Some people call it like a reverse Poincare inequality, to establish an iteration scheme that shows that the oscillation of your function has got to diminish, and this is where he gets his Holder continuity from, right? So this is more or less exactly what he then tried to do 4 years later in 1961, but no longer with functions, now with sets. So he's doing PDEs with sets, right? So his first, this is a slight typo. This is correct, but this is not what I wanted to write. His first step, just as before, right, is to show that, okay, we have some sort of bounded solution. Oops. Right, so transitioning frameworks to look at sort of boundaries of Khachapli sets for a moment. It's just much easier to write. I apologize for the changing of framework, but he's going to show that, okay, well, we can zoom into some scale where the boundary of my Khachapli set, which is a local minimizer, absolute minimizer, is going to be contained in some nice tight tubular neighborhood, so it's almost flat. This is starting to look good. Almost flat implies smooth. But actually the right analog, the thing that I wanted to write here for local boundedness, right, is more akin to what we had here, where we say that V is bounded, where V is the derivatives, right? And here this is just like the height of the boundary. So this is sort of zeroth order, but we want a boundedness of derivatives. And what that would look like is saying that actually this boundary in some small ball was Lipschitz. And he doesn't get that, but he gets that it can be covered or approximated very, very well by some Lipschitz graph. And then he uses that Lipschitz graph to get a Sobolev inequality on his boundary, and he also uses it to get, and the minimality condition, to get his Khachapli estimate. And then instead of showing that his directional derivatives have some oscillation decay, instead he's looking at what we call the tilt excess, which, if this is the normal derivative on the boundary of our set E, right, this is like an L2 average of the difference of the normal from some fixed V, and we can of course take the infimum over all directions V, right? And so I mean, clearly if this is 0, right, then we're flat. So this is our notion. This is the quantity that captures in some sense the derivatives, here realized as the normal to our tangent planes, that they're going to decay, and he indeed actually gets this sort of Holder decay, and that's how he's able to prove that these area minimizers are actually locally given by the graph of a C1 alpha, because the normal is going to be Holder continuous in a smaller ball. That's the big background. Before I move on to that, this strategy has been incredibly influential. Just as DeGiorgi's solution of, and Nash and Moser's solution of Hilbert's 19th problem has been generalized to sort of what are now called DeGiorgi classes. Basically anything that solves a Caccioppoli type inequality will then give you the kind of regularity that he originally worked out for these solutions to the divergence form elliptic bounded coefficient case. This regularity theory, this strategy, has also been adapted in codimension 1 to basically anything that's like almost minimal. So we've sort of left calculus of variations. There's no more variational framework. There are notions of almost minimality that work for which this regularity theory works. And it's very much analogous to sort of DeGiorgi classes for functions, almost minimizers for this now set or measure theoretic framework. Okay, why only codimension 1? Because if you go to higher codimension, this is like the real part of, let's say, like some two complex variables. I get some surface. We can think of this as the real part where k here is 1. This will be a critical point of the area functional. If I put any k here that's an integer, positive integer, so 1, 2, 3, 4, blah, 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 I'll also get a critical point for the area functional, some minimal surface, even though it's not truly a minimizer. And for k bigger than strictly bigger than 2, so 3, 4, 5, 1700, these will actually be stable. They will be true local minima. And if I have a high k, then I'm going to decay like some power. And you no longer have that flat tangents mean you're regular, right? If k is 3, then I will have a flat tangent, but it'll be 2 sheets coming in very close to each other. And so in higher codimension, you no longer have a good way to characterize just by whether you have flat tangents or not. So that's why this really only works for codimension 1. Okay, that's the background of regularity theory. And regularity theory for varifolds really starts from that theory and trying to develop a version that works in higher codimension and in the slightly different framework of varifolds. I'm going to have some standing hypotheses. I'm going to have a generalized mean curvature that I'm going to assume is in LP, where my measure is the mass of the varifold. As P varies, we're going to see very different behavior on the geometry of the varifold. And I'm also going to assume that the density is bounded away from 0. Let's just normalize things so that it's bigger than or equal to 1. This is to avoid some very unfortunate things that can happen if you allow your density to go to 0. And now I'm going to consider a quadratic tilt excess. Again, this L2 average of how things tilt, where now these are sort of projection operators depending upon what my tangent space is. This is the varifold analog for an m-dimensional varifold in Rn of this tilt excess that we had defined before. We should again think of this as telling us something about the derivatives of a function were our varifold given by the graph of a function. Okay, so it's also very helpful at this point to consider the functional analog of the regularity theory. And the one easy way to do this is to consider the weak Laplacian. So we suppose we have some function in W11 and that this integral is bounded. Then again, as before, Ries representation theorem tells us that we have a weak Laplacian. It's representable by a radon measure. If we assume that that radon measure is absolutely continuous with respect to Ln, this is the analog of assuming that your generalized mean curvature is absolutely continuous with respect to your varifold mass. Then we get a radon-Nikodym derivative. Let's call it G. And we're going to assume G is in LP. That's exactly these assumptions right here, but now sort of in functional form. And we should think of what this function as the radon-Nikodym derivative of our weak Laplacian. This is going to function very much like our mean curvature. And we know from just Sobolev regularity, right, that therefore our function f is actually going to be in W2P because we assumed that G was in LP. And therefore, depending upon P, we're going to get very different behavior, right? So we have Mori estimates that tell us if P is in the supercritical case, where n is our dimension. Then we have some Holder continuity on our derivatives. Stein proved a lovely theorem that said, that, okay, if we have P in the Lorentz scale, ln1, then actually we get continuity. But if we have P equals n, which would be ln n, if you're following the Lorentz scale, then we get VMO estimates. And if we're strictly between 1 and n, then the usual Sobolev-Gagliardo-Nuremberg estimates give you that df is actually in some higher LP space, right? Basic things. And this, I want to emphasize, is exactly the picture that we should expect for the case of the generalized mean curvature, right? So the first part of this filling in this picture for varifolds came in 1972, where Allard proved the following remarkable theorem. So we have m and n are integers. We have some rectifiable varifold of dimension m in Rn, and suppose that we have some small epsilon, p is bigger than m, so we're in the supercritical case, and we're going to assume again that our density function is bounded away from, is bigger than or equal to 1. We have density control at scale 1. We don't have too much mass, and then we're going to assume that our LP norm of our generalized mean curvature is very, very small. And as long as that's small enough, then actually there exists some function, the C1 alpha, such that in a smaller ball, the support of our varifold is actually given by the graph of that function, right? So this is exactly this supercritical case for functions, now for varifolds. And later in '86, Dugan improved this and showed that actually this function would be in by W2P. Okay, the theorem that actually makes the theorem work is precisely this sort of decay rate on the tilt excess, right? As you would expect. Okay. The main ingredients are, again, first Allard needs to obtain some density control, then he obtains a height bound, and then he goes through a lot of work to get this Lipschitz approximation. This Lipschitz approximation is, again, going to give him a certain Sobolev inequality, and then he's going to use the fact that if epsilon is very small, this Lipschitz approximation should be really close to a harmonic function. And then he's going to use the fact that it's close to a harmonic function to use sort of more traditional harmonic estimates to get his tilt excess to decay at a certain rate. Where again, this Lipschitz approximation is doing the vast majority of the work here. Okay. So this is how to generalize, in some sense, DeGiorgi's solution to Hilbert's 19th problem to the case of varifolds. A natural question, though, is what happens if we're not in the supercritical case, right? So good things and bad things. If we're strictly below our dimension, then things blow up. You can have supports of your varifold which are highly disconnected, dense in some neighborhood of the origin, all the while trying to satisfying these four hypotheses, just with now p strictly less than m. Right? So things can go bad. It's not so hard to see this. You just take spheres and shrink them and place them where you need to, and you can get everything to work out. So this tells us that absolutely no global regularity is possible in the subcritical case. But that leaves a lot of open questions. For instance, might the support still be approximately quadratically approximable almost everywhere? Might the support be countably C2 rectifiable? Might it look like pieces, infinitesimally pieces of C2 submanifolds? Can we get some rate of convergence almost everywhere for this tilt excess? You should think of this as the sort of Sobolev type estimate. And more importantly, or perhaps more difficultly, instead of a almost everywhere decay rate, can we obtain a uniform decay rate, pointwise everywhere? right? What's the optimal rate of decay there? And I think for time reasons, I'm going to move through this pretty quickly. But there's this beautiful body of work starting with Kenneth Bracke in '78 and going through Schatzli and Ulrich Menne, where they worked out this sort of Gagliardo-Sobolev-Nuremberg regime estimates, this beautiful relationship between this subcritical case of the generalized mean curvature and how the tilt excess decays. And some very surprising things in this are, for example, you can have a C2 rectifiable integral varifold, which you should think of as very nice. And you can have, if your generalized mean curvature is in some low enough LP space, then you can't assume that you get sort of order row decay, right? Which, if you think of as having a C2 rectifiable manifold, you should think you should have a second derivative. You should get, right, this order row because you want to have a quadratic approximation, but you can't assume you get it everywhere. You can have points where things go just right and you miss it. Okay, that was a pointwise almost everywhere story. They've also worked out the optimal rates for decay, pointwise everywhere, right? So very much this subcritical situation was worked out largely in the 2000s and 2010s. Okay, so that only leaves the critical case. What happens in the critical case? This is the really hard one. I'm going to call these set of assumptions the critical Allard regularity regime. So assume that V satisfies the standing assumptions, meaning we have a generalized mean curvature in some LP space, and we're assuming that our density function is bigger than or equal to 1. And now the origin is in the support of the varifold, and we have this tight control on the mass. So we're very close in terms of mass to a flat disk. And we have epsilon control on the MLM norm of our generalized mean curvature. Under these assumptions, right, we might ask what sort of regularity holds. Well, in 2 dimensions, we're now assuming that our generalized mean curvature is in L2, right? This is basically the Willmore energy, and there's a huge literature investigating the Willmore energy. There's no way I could include all of it. I do want to mention that Tatiana Toro in '94 attained by Lipschitz parameterizations for certain classes of integral varifolds under very similar hypotheses to our critical Allard regularity regime. And very, very recently, Yuchen Bi and Jie Zhao obtained by Lipschitz parameterizations by W22 functions for general 2-dimensional integral varifolds under these assumptions, right? Under this regime. This is a very beautiful paper, but it also relies upon complex analysis, isothermal coordinates, things like this. So there's no chance of generalizing this beautiful result to higher dimensions. Instead, the result that we might think to generalize came a year before, so 2022, where Jie Zhao showed that if we have some rectifiable varifold, again, 2-dimensional, and we assume that we're in the critical Allard regime, Allard regularity regime with small epsilon, and this extra assumption that says that our generalized mean curvature is actually perpendicular to our tangent spaces almost everywhere, which is the same as saying that the, at least on connected components, the density is constant, right? So that's what this condition says, that under these conditions, well, then as long as epsilon is small enough, then we get some bi-Holder image of a disk to cover the support in some smaller ball, right? And this is, in a sense, what we should try to generalize to higher dimensions, but there are some problems. The methods that they used cannot be generalized at all. There's a very specific monotonicity formula that basically works because 2 minus 2 is 0, and like n minus 2 is not 0 for n bigger than 2. So and this this monotonicity formula only works for two-dimensional rectifiable varifolds. You cannot generalize it to higher dimensions. It just doesn't work that way. And furthermore, this assumption of perpendicular mean curvature, right, in some sense cannot be removed. Because there's an example by Ulrich Menne where you take some plane and then you fix spherical caps that are sort of very delicately calibrated, right? And you need, you have to allow your density to sort of increase in order to compensate from the pull of these two extra arms, so that the density on this side, right, sort of outweighs the density and the mass on that side. And notice as your spherical caps get flatter and flatter and flatter, right, you're going to pick up a what? Like if this is a theta, you're going to pick up like a 2 cosine theta, like 1. That's the amount of pull sort of on this side. And so as theta gets smaller and smaller, this is going to approach 3. And so you really need your density to be able to go up to 3 to make this work. But if you allow rectifiable varifolds, which is what we're doing, and we can allow our density, right, to sort of move continuously between 1 and 3, no problem, then this example gives us, can be used to construct an example that will satisfy the critical Allied regularity regime, but which of course has non-trivial topology in every neighborhood of the origin. The density goes to infinity, all hell breaks loose, right? So in some sense, we can't consider just general rectifiable varifolds. And the, in my opinion, correct generalization of this two-dimensional result is the following. Oh, well, I already asked those questions. How do we generalize this to higher dimensions? Can we really not allow theta to vary? The answer is going to be we can let it vary a little bit. So this is the theorem that I think is the proper generalization to the higher dimensional case. Came out last year. So again, we have some varifold. We're going to let it be a rectifiable varifold. We're going to satisfy the critical Allied regularity regime for some small epsilon. And we're going to allow our density to sort of wiggle by some gamma theta parameter, right? And of course, for n large enough, these intervals will overlap, and then you'll be allowed for anything. But most importantly, at least around n equals 1, right, we're still trapped between 1 and 1 plus gamma, much as in Allard's original supercritical regularity theory, right? So if we satisfy these hypotheses, then our tilt excess, right, sort of the best approximation to our tilt excess, point-wise everywhere in some smaller ball, the limit goes to 0, right? So this is the VMO estimate for varifolds, right? This is from the Sobolev embedding regularity theory, right? This is the version that carries over to this varifold regularity. And in fact, you can obtain something like a rate of decay. This result is sharp in the following sense. There's an example of some varifold just given by the graph of a nice Lipschitz function, which is going to oscillate very, very slowly as you go towards the origin. Basically throw in like a log, like sine of log of I think you need 2 or 3 logs, I can't remember, in your oscillation, such that it satisfies the critical Allied regularity regime, and you can make it satisfy it for any epsilon you want, and it does not have unique tangents at the origin, and you actually get this same rate of decay pointwise everywhere, right? This is our sort of maximum rate. And so it's important to note that this lack of unique tangents is allowed in this estimate because we're only looking at the sort of best approximating subspace, and that subspace at different scales can turn and rotate and do all sorts of things, right? So we're not getting graphicality out of this. We're just getting this VMO style decay on what we should think of as roughly our derivatives. Okay, but we do get something almost like a graphical parametrization. There exists some map such that the support is contained in the image of that map, and that map will be by W1P, where P here is some function of tau, and there's some rate on sort of how regular you can take your map, depending, of course, upon your how small you're willing to take epsilon. Right? So given some t, you can find epsilon small enough such that this holds. Okay. I should also note that this corollary depends heavily upon previous results from that Yu Chen B and Jie Zhao paper, which was just in the two-dimensional case. Their parameterization results do carry over, right? It was just their original estimates relied upon complex analysis, so we couldn't use those. The proof of the theorem is actually basically exactly the same as the standard proof of Allard's tilt excess decay theorem. Again, you get some density control, you get a height bound, you get a Lipschitz approximation, you use this to get a Sobolev inequality, you use then your Lipschitz approximation again to get your Kachapoli inequality, and therefore compare with harmonic approximations and obtain the same sort of style. The reason why it took until last year in order to solve the critical case in all dimensions and all codimensions is that there wasn't a good enough Lipschitz approximation. The original Lipschitz approximation by Allard only worked with a certain estimate that would never hold in the critical case. There were some improvements in Lipschitz approximations by Brachy and others, but it really wasn't until 2013 that Ulrich Menne proved a Lipschitz approximation suited for the critical case, and this was the key tool to make this entire machinery go. Right, so that's why it took so long. Okay, how much time do I have? Perfect. Okay, so some open questions. I'm really curious in how large we can let this density parameter go. We know we can't let it go to 1. There are examples, but we should be able to let it go, to anything strictly less than 1, and then find some epsilon for which this works, because it's basically saying that, like, well, if you let it go almost to 1, right, then maybe you might have some of these outer shells. But if you let epsilon be small enough, each of these shells costs a certain amount of mean curvature. And so if you let your epsilon be small enough, you could only possibly have the smaller shells. But this would eliminate the possibility of any of the smaller sort of shells actually working out. That's the hope. There's other questions about, can this improved Lipschitz approximation allow for an extension of the previous subcritical theory to these these almost integral varifolds where we allow the density to change. All of the previous results were only for integral varifolds, and there's some very fundamental results that we don't have for just rectifiable varifolds where we're allowing our density to change. For example, in a smooth submanifold, if you have some like C1 density on it, then your mean curvature will have like a tangential component, which you can think of as the geometric part from the shape, and it'll have a tangential component, which will come from the derivative of your density. And we don't know that for varifolds, you can make that decomposition. Very fundamental questions still to be answered for rectifiable varifolds. I will finish with some broader open questions. I think I'll start with this one. I've tried to pitch this talk as we're trying to do like basic elliptic regularity theory, but now with varifolds, right? There was this picture for Sobolev regularity, and now we have more or less filled it in finally for varifold regularity. But there's the whole rest of like elliptic PDE estimates that you can wonder, how does it translate over to the varifold case, right? Can you, for example, instead of bounding the Hessian by the sort of right-hand side in a Poisson equation, right? Can you can you apply, bound the second fundamental form by some constant times the integral of your generalized mean curvature, things like this. So that's sort of the program going forward. And also in an ongoing project, we're trying to develop elliptic PDEs on varifolds, which is startlingly different from like PDEs on manifolds, because one of the most important, sorry, I need something else. I want this. One of the most important parts of like the elliptic regularity theory is you have some test function and you want to say, it looks like this other function. I can add two functions together and I still get a function in my space. But the analog of Sobolev functions on manifolds, because of the interesting topology, you cannot always add two Sobolev functions on varifolds and actually get another Sobolev function on varifolds. You could have a function which is constantly 1 on this segment, and another function which is constantly 1 on this, and this segment, right? You cannot add them and get another sort of Sobolev function on this beautiful, like, minimal varifold, because you will have a jump at the origin, right? This is more like a like a bounded variation type function, but it won't be the right analog for Sobolev. And so trying to develop an elliptic regularity theory on varifolds where you have such fundamental problems as this is really an exciting project going forward. And I think I'm probably 2 minutes over. Sorry. Yeah.
So thank you for a nice talk. Any questions, comments?
So what can you model with the elliptic PDEs in a varifold? So
yeah, so it's not just abstraction for abstraction's sake. On nice manifolds, you can look at like the distance function. So you can take like some tubular neighborhood. If you're I don't know, like a C2 submanifold, you can take some tubular neighborhood, and you can look at or some ball, and you can look at the distance function, and that distance function will carry information about the mean curvature vector. And so this is the goal is to apply the sort of general elliptic PDEs on varifolds framework, in particular to distance functions, to obtain estimates on the distance functions so that we can really estimate. You know, we have like sort of it's not too hard to get like L infinity estimates, and maybe your varifold does something inside, but much finer estimates on the distance function, right, from sort of the complement out here, would allow for finer understandings and perhaps finer regularity statements about the geometry of the varifolds. So that's the immediate goal.
Any other question? So in your theorem, you obtain an upper. I'm somehow lost because you obtain an upper bound, but then you say that there is exactly, is it related? So it's exactly this behavior. So it's upper bound, and it's exactly this behavior.
Yeah, I mean, there's
Log.
yeah, there's some constant of comparison.
Because in this next slide, you say that there is.
Yeah, so the example which shows that it's sharp.
Exactly. So yes, but I mean, can you prove that this is exactly this or not?
Can this statement be proven?
No. In the previous, the estimate is. Can it be improved to? Can you prove that it is exactly this behavior, or not?
Yeah. So this statement is a little bit complicated. We're looking at the best approximating plane at a point x in its scale r, and then we're looking over an entire all of the points in the support of the varifold in some ball. So this is a uniform estimate pointwise, every single point in your varifold under these assumptions, right? the tilt excess must decay at least like this. The decay rate will be much better for almost every point, right? Simply because almost every point will be a Lebesgue point, and therefore you'll get a certain rate of decay on your generalized mean curvature, and that will improve this rate of decay for almost every point in your support. But the point of this statement, these two statements, is that actually that I've obtained an estimate for every single point pointwise. They must decay at least this rate, and in fact, by example, there are examples of varifolds which satisfy the hypothesis, where at certain points, in this case the origin, you genuinely achieve that rate of decay. Right? So, but for almost every other point in this example, you'll have a much faster rate of decay. Yeah, but the point, the importance is that this is the supremum over all points. It's not a statement in measure. It's pointwise everywhere. Yeah.
Other question? So if it's not the case, let's thank Shane.
Okay, thank you all very much.